So today we're going to be looking at linear regression. And just to give you where we are in the roadmap, we're in this sequence of lectures where we're teaching you about linear regression. Monday. On Wednesday, we talked about linear associations and the correlation coefficient. Today, we're going to be talking about how you can use a linear association to make predictions. If you find a linear association, there's a relationship between two variables. And if you know one of them, you can use that association to make a prediction, a best guess at the other. And then we'll continue next week. You'll look at least squares, which is a method for finding the best line that fits the data, and then some more sophisticated topics working with linear regression. So that's where we're headed. Let me give you just a brief review of where we've come. Last lecture, we talked about correlation. And correlation is a measure of how strongly related two variables are, how strong a pattern is when you have a linear association. So here are some plots, and you can see when the correlation coefficient R is 0, there's no correlation, there's no association. And when the correlation coefficient is close to 1, that means there's a very strong association. Knowing the value of one of the attributes really narrows down the possibilities for the other attribute. They fall very close to a line. Okay, so correlation coefficient measures linear association. We showed how to compute it using standard units. It gives you a number between -1 and 1. When it's 1 or -1, that means it's a straight line. When it's 0, that means there's no linear association, and values in between kind of interpolate between that. And as a reminder, the definition of the correlation coefficient R from last time, the way you compute it is by converting X and Y to standard units. Then you, for each data point, you take the product of the X times the Y value, and you take the average of that. And what this ends up doing is values that are in the upper right quadrant or the lower left quadrant pull this average up. They contribute positive values, which is kind of means that a line that's heading this way will increase the value of this average. And values in the other two quadrants will contribute negative values because you're multiplying a positive X times a negative Y or a negative X times a positive Y. Those contribute negative values to the average. So they pull the average down, which is kind of intuitive. If you have a line sloping this way, that's a negative association, and it will lead to a negative average and a negative correlation coefficient. So that's kind of intuitively what the correlation coefficient is doing. This measures how close the scatter plot is to a straight line. Okay, so here's your how are we doing so far test. I've got 4 pairs of scatter plots, and I want to know for each one which has a larger value of R, like more positive, bigger on the number line. So why don't you write in the chat something like LR, LL, or whatever. L meaning it's the left of the two, and R meaning it's the right of the two for A, B, C, and D. So take a moment to think, and then you can do this for all 4 of them, and maybe leave me a private chat message if you want. Okay. This is a little tricky. Some of these are a little tricky. So let's start with part A. Which of these has a higher value of R? Lots of you were saying the right one does. And I'm with you on that. The correlation coefficient for the left one is probably about 0. I don't see much of a association. And for the right one, there's a positive association. So the correlation coefficient might be a half, some fractional positive value. In any case, bigger than 0. So for A, the right one is correct. For B, let's look at B. For B, we've got some kind of positive association here for the left one and another positive association. Let's figure out which we think has a larger value of the correlation coefficient. They both seem kind of roughly similarly close to a line. They're about equally clustered to the line, except that there's these few points over here. That's kind of the main difference. So what are these few points over here going to do? The slope for the left one's kind of be like this, and the slope for the right one's going to kind of be like this, but there's these points that are kind of pull it down. These points over here are going to contribute to a negative value of the correlation coefficient because X is positive, Y is negative. When you take their product, you get a negative number. That's kind of lowering the value of the average, so lowering the correlation coefficient. So the correlation of the left one, I think, is gonna be, yeah, it's gonna be higher. These outliers, I think, are gonna reduce the correlation. Okay, let's look at part C. Part C, there's a much stronger association for the left one. The right one has a weaker association. So if we put that in numbers, for R, what might you expect to see for the correlation coefficient for the left one? Well, it's something pretty strong, but it's also a negative association. So it's close to -1, like maybe you're thinking -0.8, -0.9, something like that. And then the right one is also a negative association, but not as strong, maybe -0.5. So here, this is a little tricky, but the right one has a larger value of R, even though it's a weaker association. Okay, because -0.5 is a little more to the right on the number line. Okay, part D, left one, that's kind of a negative association to R, maybe, I don't know, -0.5 or something. And what about the right one? What do we expect to get for the correlation coefficient here? Well, it's kind of got some of those same points, but then it's got these outliers over here. So it's not clear what correlation coefficient you're going to get for the right one, but it might be something close to 0. There's not like really a clear trend. It might, it's kind of like there's some things that are pulling it towards a positive and some that are pulling it towards negative. And I bet those are going to average out, and I bet your correlation coefficient is going to be close to 0 for the right one. So the correlation coefficient -0.5 and a 0, let's say, the 0 will be larger. So the right one will have a larger value of R. Okay, let me just check and see how you're doing on that. Any questions? Why is C the right one? Because even though there's a weaker correlation in the right one, it's actually a larger value of R. It's like maybe -0.5 versus -0.8, and -0.5 is larger. Okay. Why is D right? Similar reason. Probably about -0.5 for the left one, probably about 0 for the right one. So 0 is larger than -0.5. Little tricky. Yeah. All right. So as a reminder, I wanted to give you some things to be careful about for when you interpret R. You can usually interpret R as a measure of how strong the linear association there is. But be wary, just because there's association doesn't necessarily mean there's causation. If there's nonlinearity, R might not be a good measure of association. It only measures linear association. Outliers can really mess it up. And there are ecological correlations. The ecological fallacy, just because you see a correlation or an association at a group level doesn't necessarily mean there'll be one at an individual level. So let me give you one more example. And I need to fix how I share my screen for this to work. Okay, give me a moment here. Working on it. Okay. Notebook time. All right, so I thought I would show you an example from the 2020 election. I hope you're not sick of elections, but I got some data from the preliminary vote count so far that's been reported in the news, and we're going to take a look at that. So I put it into a spreadsheet, and I've typed it all in before a lecture. And here we have here for each state, the percentage of people who are currently, according to currently reported results, are reported as voting for Biden. And we're going to look at the relationship between that and the median income in the state. And my information on the median income is a little out of date, but probably won't have changed too much. So put that into a single data set, and then we're going to do a scatter plot. And here's what the scatter plot looks like. So just visually look at this data set and tell me what your interpretation is based on the scatter plot. Do you think there's an association here? Yeah, positive R, some kind of a weak association, some positive association. All right, yeah, so the interpretation here is, if we try to say it out loud, it looks like there's an association between median income and the percent who are voting for Biden in that state. That looks like a pretty good association, pretty good correlation there. So quick sanity check time. Does what we're saying is higher income means more likely to vote for Biden? Does that sound right to you? Something seems off here. Is my data wrong? Is there something wrong with my data set? No, it's not the data set. The problem is my interpretation. Each dot here represents a state. This is state level results. So actually, if I was being a little more careful, what this shows is that states with a higher median income are more likely to have higher vote share for Biden, and states with a lower median income, poorer states, are likely to have a lower vote share for Biden. Now, that's a little weird. If you know something about politics, you might know that's a little weird, because here's a party affiliation broken down by income. And if you look at this this plot here, we can see, many of you, if you're a political junkie, you probably know this, that poorer folks tend to be more likely to vote for the Democratic candidate. So you see this weird thing where at the state level, the poorer states are more likely to vote Republican, but at the individual level, poorer individuals are more likely to vote Democratic. So why is that? Why does that happen? Maybe it's the education level in the state. Cities, yes. There's a confounding factor. Urban versus rural, population density, population, exactly. We have some states that are more urban. They have more cities, higher population density. And that tends to correlate with a lot of things. The higher density, the more cities, urban areas tend to vote more Democratic. They also tend to be wealthier areas. And so states with a high population density, with a lot of cities, are more likely to have a higher vote share for Biden. They're also likely to have a higher median income. So that's what we're seeing going on here is basically there's a confounding factor. So the ecological fallacy here is the mistake of assuming that just because there's an association at the state level, that means the same association happens at the individual level, and it doesn't. It's just like the SAT example that I showed you before. Okay, so just be careful when you're aggregating data and looking at associations. All right, here's another one to be careful about. Here's a plot of chocolate consumption per person in each of a bunch of countries, and the number of Nobel laureates per 10 million people in that country. And what do you notice? I'll tell you what I notice. Where are there lots of high percentage of Nobel laureates? Switzerland. Where is there a high consumption of chocolate? Switzerland. So does this mean that if I want to win a Nobel Prize, like time for some candy bars? Yay, Halloween? Chocolate equals big brain. No. It's just showing that there's an association. But that doesn't necessarily mean that eating chocolate makes you smarter. There could be any number of other confounding factors. Like Switzerland is different from other countries in a lot of ways. They're a very wealthy country, and you could imagine that higher income would correlate with more disposable income, so more luxuries, so more eating chocolate, and would also correlate with like better education systems and more opportunities and more Nobel laureates. Okay, so here's a little Halloween picture for you. You want to see something really scary? There you go. There's your Halloween picture. A week late, sorry. All right, discussion question for you all. Let's start with number one. True or false? If X and Y have a correlation of 1, then one of them must cause the other. True or false? False. No, not true. That would be making the mistake of thinking because there's a correlation that there must be causation. Okay, good. All right, number 2, true or false? If the correlation of X and Y is close to 0, then knowing one will never help us predict the other. Yeah. Okay. Okay. Good. Good. I'd go with true. If the correlation is close to 0, oh, wait. Oh, be careful. Be careful. This one's a little tricky. This one's a little tricky. I almost got caught by this. I was about to say true, but actually there's a problem. If the correlation is close to 0, then there's no association, so one won't help us predict the other. What's wrong with that? That's actually not correct. There may be another pattern like a curve. Ah, yes. If the correlation of X and Y is close to 0, that means there's no linear association. But there could be still a nonlinear association. You could have a nonlinear association, a kind of a bowl shape, and it still end up with a correlation coefficient of 0. And if there was a nonlinear association, like a bowl shape, for instance, then knowing the value of one of them would be very helpful for predicting the value of the other. So actually, number 2 is totally false. Totally false. Okay, number three, true or false? If X and Y have a correlation of negative 0.8, then they have a negative association. Okay, okay. I buy it. I buy it. I buy it. I think, okay, so I'm with you on true. I think you might want to look at the scatter plot just to confirm that the shape looks like a linear association. And make sure it's not some crazy shape. But as long as the shape looks like a linear association, then a correlation coefficient of negative 0.8 would mean a negative association. Very good. Okay. I heard that my Wi-Fi may be lagging. If other people are finding that I have bad quality video or audio, please let me know and I'll make some adjustments here. Oh, it's bad. Okay. All right. All right. We're gonna take a moment and I'm gonna move closer to my Wi-Fi. And we're gonna try to fix this. Okay, give me a moment. All right, let's try now and see if this is any better. I just moved a little closer. Tour of the house. Maybe another time. Here we go. I want to switch to. Oh, can I go over part 2 again? I cut out for part of it. Absolutely, yes. Part 2 is tricky. All right, part 2 is very tricky. Here's the deal. If the correlation of X and Y is close to 0, that means there's no linear association. But you could still have a nonlinear association. You could still have like a bowl shape, a curved shape. And that kind of shape could still lead to a correlation coefficient of 0. So there could still be a nonlinear association. And if there is a nonlinear association, then the value of X would be very helpful for predicting the value of Y. Okay, so correlation coefficient of 0 rules out a linear association, but it doesn't rule out a nonlinear association. It was tricky. It got me for a minute. Okay, so I want to move on now to prediction. If you have an association between two variables, if you have a linear association between two variables, and you know the value of one of them, you can use that association to help you make a prediction, a best guess at the value of the other variable. Okay, so let's look again at this data set we've been looking at a bunch, which is this Galton heights of kids, and talk a little bit about how we can do prediction. I talked about this notion before of nearest neighbor regression. So just a review of how that works. Let's suppose we know the height of the parents, and we want to predict what the height of their children will be. What we're going to do, if we have a particular couple in mind, let's say a couple whose heights average to 68 inches, and we want to predict how tall their kid will be, is we look for other couples where we know the heights of their kids. They're similar. And we figure that the heights of the kids will be related. So we look at all the other couples whose height is close to 68 inches. That's all the blue dots between these two red lines. We look at the heights of all of their kids and we take the average, and that's our best guess at what the height of the kid of a new couple with a mid-parent height of 68 inches will be. So this is how you get a prediction. And if we do this for every mid-parent height, you get a yellow line for each, just kind of scan left to right and draw a yellow dot for each, then we get this yellow shape here, which is kind of a curvy shape, and I'm going to call it a prediction line. It's not really a line. It's kind of almost a straight line, but it's a little squiggly. So this is known as nearest neighbor regression. And the way it works is given an X value, if you want to make your best guess at what the Y value associated to that is, you find other similar nearby X values in your data set. You look at the corresponding Y values for those similar ones. You average their Y values, and that will be the prediction. So the prediction for an X value is the average of the Y values of the similar points. And you could make this prediction for any X value. So if you sweep X from the smallest to the largest possible value, that gives you a bunch of predictions, and you could draw a graph of that. And we could call that prediction line, or the graph of averages, the nearest neighbor prediction line, the nearest neighbor regression line. I'm calling it a line, even though it may not be a straight line. And if the association between X and Y is linear, then this graph will tend to fall approximately on a line. Like we saw, those yellow dots fell approximately on a line. It was a little bit squiggly. Okay, so we're going to now do an exercise where we apply this technique to some synthetic data sets I've constructed that have a particular strength of correlation. Okay, so this one here has correlation coefficient 0.99. So a very strong association. And I plotted it in standard units. And here's another one that has no correlation, no linear association. R is 0.0. And again, I plotted this in standard units. And I'm going to walk through some examples, and we're going to see what that prediction line looks like for different values of R. How am I doing now on my Wi-Fi? How's my audio and my video? Is it good? Is it bad? Yay! All right, glad to hear that. So notebook time. All right, we're gonna look at some synthetic data sets, and I pre-coded up some code to generate me a synthetic data set that's known to have a correlation coefficient of 0.99, but is otherwise random. And here's what that looks like if we scatter plot it. And I generated the data and kind of put it into standard units. So this is in standard units. All right, so you can see 0.99, that corresponds to points that are very close to a line, very closely clustered along a straight line. What this code is doing is generating a synthetic data set. This is not real data. It's just data that was randomly generated by a particular procedure that's designed to give you data that has a correlation coefficient of 0.99. Okay. So now we can take this nearest neighbor regression approach, which I showed you last lecture and summarized just now. Given a value of X, if you want to make a prediction, if I have a new data point when I'm told only the value of X and I want to make a prediction for what the value of Y will be, basically I go look at that X value, say X is 1. I go look at similar points in here with an X value near 1, and I average all their Y values. So that's what this code here is doing. And for instance, we can do an example here. If I wanted to make a prediction for x equals negative 2.25, you would expect it to be somewhere around y value a little less than negative 2. And indeed, we find the predicted value for y is negative 2.14 using this nearest neighbor technique. Yes, nearest neighbors regression works for both linear and nonlinear associations. That's one thing that's pretty cool about it. Why can't you take the average of the single x value? Why do you have to include the neighbors? Well, there's kind of two reasons for that. One reason is there might be no data point in this data set that has an x value that's exactly matching. You might have ones that are similar, but not exactly equal, because here x is some continuous thing. And you might find negative 2.24, but you don't find negative 2.25. And the other reason is there's some noise. You can see there's some noise in these points. There's some kind of like variation about where they are. And if I picked a single point, I might, if I was unlucky, just happen to pick one that was on the high end or on the low end. Whereas if I'm picking similar points, like getting 10 or 20 similar points, some of those will be on the high end, some of those will be on the low end. And when I average them out, those should cancel out and I should probably get a better estimate, a better prediction. So that was a choice. It's a kind of an arbitrary choice. You don't have to do that. It's just what I happen to do. Yes, this was just an example. This value here is an example. There's you could vary that. It could be 0.1, could be something smaller than that. Yeah. So don't worry too much about exactly how you would set this value. Yeah, we'll look at a correlation of 1. We'll look at different values of correlation, but let's just look at this one. I want to dig into this correlation 0.99, and then we're going to change the correlation coefficient and do it all over again and see what happens. So I'm going to put onto this graph display the graph of averages. This nearest neighbor regression predictions for all values of x. And here, as you can see, the yellow is the predictions that would be made by this nearest neighbor technique. And you can see they follow kind of almost exactly on a straight line. And they're doing something kind of intuitive. They're fitting a line that kind of goes through the middle of the data. All right. So we're envisioning the data is mostly basically follows this line, but there's a little bit of noise. There's a little bit of variation that's each data point might be a little bit off from the line. Okay, so given the blue dots, the nearest neighbor regression gives me the yellow dots. It gives me a way to make predictions. So there's the predictions that nearest neighbor regression would give you. And you'll notice it looks almost straight. It's a little bit squiggly, especially on the ends where there's not a lot of data, but it's almost straight. Now, in a lot of settings, actually, we have some reasons to think that probably if there's a linear association, then probably the correct prediction line should actually be a straight line. Nearest neighbor regression didn't give me a straight line. If we know that a linear association makes sense, if we look at this graph and see, wow, it looks like it's close to a line, maybe it would be better to have predictions that fell exactly on a straight line. That might give me more accurate predictions. So this is kind of a shortcoming of nearest neighbor regression. So let's look at if we tried to draw a straight line that fits this data that goes through these points. Let's try some values. So we could try a straight line here. I've drawn here in blue a straight line with slope 1. And how does that look to you? Does that straight line looks like it, the blue line looks like it fits the data? Yeah. Yeah, it looks pretty darn good, doesn't it? So if you were going to make predictions, maybe it would be a good idea to make a prediction by taking your x value and looking up the corresponding point on the blue line and making your prediction from the blue line instead of the yellow line. That'd be a perfectly reasonable procedure. So this process of trying to find a straight line that goes through the data is called linear regression. Why would a straight line be better? Well, in this case, there's not much difference between the yellow line and the blue line. So for this particular example, it's kind of not clear why we would prefer one over the other. Now, I'll show you some examples where maybe it'll make a little bit clearer why a straight line might be better. One reason why a straight line might be nice is if you believe that there's probably a linear association, like between housing prices and the square footage, you imagine that there's probably some kind of close to straight line situation there. Then I've got some data around here. I can kind of extrapolate. I can handle well, make predictions even that are a little bit outside the range of where my data set is. Okay, so let's do this again. We're going to do it again, but now with a different value of the correlation coefficient. So now I'm going to do the same thing, but I'm going to do it with a correlation coefficient of 0. So there's a random synthetic data set that's generated of no correlation coefficient of 0. There's no association there. And you can just visually looking at that, there's no clear trend line. They're just X and Y seem to be two separate values, and knowing the value of one of them doesn't really help you predict the value of the other. So we can still apply this nearest neighbor prediction with this data set, and we'll draw that. As soon as the computation finishes running, we'll draw that. Takes a while, it's a little bit slow. And you could think while it's waiting, what do you expect that prediction line to look like? So there's the yellow, that's the predictions made by the nearest neighbor technique. It's not quite a straight line. It's kind of close to a straight line. It's a little curvy. It's especially curvy on the ends where there's not a lot of data points. That makes sense because on the ends, we're trying to make a prediction and there's not many similar data points. So we're really affected by the 1 or 2 similar data points we do have. We're really affected by any noise in them. Whereas in the middle, we're averaging over a lot of data points. So the noise has less effect. But still, it's a little squiggly. Now, if you wanted a straight line that might go through this, what do you think, what kind of straight line would be reasonable to use for prediction? Yeah, why is it a horizontal line rather than a vertical line? Horizontal flat line, flat horizontal line would be reasonable for prediction. So why was this horizontal rather than vertical? Why does horizontal make sense for prediction? Well, for prediction, if you think about it, in this case, a straight line, a flat line at exactly y equals 0 makes a lot of sense because I said there's no association. So knowing the value of x does not help you at all to predict y. So if I give you a value of x equals 1 and ask you to predict y, your best thing to do is just ignore what I told you about x and make a prediction for y with no information at all. Now, if I gave you no information at all and asked you to make a prediction of y, what would be the best choice for you to use for your prediction of y? 0, because 0 is right in the middle. That would kind of give you the least error on average. If you pick a value above that's positive, then you'll make really big errors if the data point happens to be below that. And if you pick a value that's negative, you'll make big errors when the value is above that. So you want a point that is right in the middle. In other words, at the mean of the the mean of the y values. When you have no information about anything, the best prediction you can make would be at the mean. And the mean of the y values here is 0. So the best prediction you could make for y is 0 if I give you no information. And if I give you some information about x, that still shouldn't change your prediction because x and y are unassociated. They're not correlated. So no matter what value of x I give you, the best prediction you could possibly make would be y equals 0. And if you draw that line, the line at y equals 0, you would get a flat horizontal line that's exactly through y equals 0. So in this case, nearest neighbor regression gave me something that was pretty close to that. I happen to know that the best prediction line I could get would be exactly straight line. And in this case, it gave me one that's a little squiggly. It's pretty close to that, but it's not perfect. Okay, so this is maybe hopefully giving you a little bit of a sense why you might want a straight line. In this case, the data set was constructed so that a straight line would be, there's a linear association. Any association at all is linear. In this case, there's no association. So a straight line makes sense for what we would like to have. Okay, so let's do it again. I'm going to do it again, and we're going to do it again until we're just absolutely sick of this. And then maybe we'll do it once more. We're going to do a correlation coefficient of 1/2 this time. So somewhere in between, we did 0.99, we did 0. Here's what the data looks like if you have a correlation coefficient of 1/2. And if you want to make a prediction at x equals 1.5, Well, nearest neighbor regression would say, look up here at x equals 1.5, find other points with an x value close to 1.5, draw the average of their y values, and use that as your prediction. Okay, so let's do that. Let's run our nearest neighbor prediction. And while it's running, I want you to make a guess for me about what you think the yellow dots are going to look like when I run nearest neighbor prediction. Is it going to look like a line or not? And if it's going to look like a line, what do you think the slope is going to be? Is it going to be above? Is it going to be like this red line? Is it going to be have a lower slope, a larger slope? Less steep, lower slope. That's right. So here's what you get. There's what the prediction line with the nearest neighbor regression looks like. When the x value is large, you're taking the average of these points here, and that falls around here. And when the x value is small, you're taking the average of these points, and that falls around here. And it just so happens when you do that process that you end up with a line that is less steep than the red one. The red one was slope 1, but here you get something that's close to a straight line. It's not exactly a straight line. And if we wanted to draw a straight line through it, then you would get the blue line. So the blue line here I drew was slope 1/2. And now you should be starting to get suspicious. I carefully chose the slope of the blue line to be as close to the yellow line as possible. In other words, I want something very like what the nearest neighbor prediction would give me, but I want to force it to be a straight line because I know this data was generated with a linear association. So the best prediction rule ought to be a straight line. And I played around with what the slope of that should be to get the blue line to match the yellow as closely as possible. And the best one that I could find was 0.5. I tried like 0.6, and that was not quite good. That was a little bit too steep. And I tried 0.4, and that was not quite good. It was not steep enough. And 0.5 was like Goldilocks. The blue line is like right lined up with the yellow line I get from nearest neighbor regression. And now maybe you're a little suspicious. I don't know if you're noticing the pattern here between the correlation coefficient and the slope of the line. What was the correlation coefficient again? It was 0.5. And what was the slope of the blue line that was kind of the best fit, best line, best prediction line? 0.5. So we're going to do one more. Maybe you're sick of this by now. So like I said, we're going to do until you're sick, and then we'll do one more. And now we'll do with 0.7, and we'll see what the data looks like. We'll see what the yellow nearest neighbor regression line looks like, and what slope are you predicting it to have? Given that r equals 0.7. Yeah, if this pattern holds up, so blue is aligned with 0.7, yellow is the nearest neighbor regression line, and ta-da, almost a perfect match. All right, so what this is telling us is that if you want to make a prediction line and you want it to be a straight line, this should make you suspicious that maybe the best line has a slope that's equal to the correlation coefficient. So if we go up and review where we started with oh, I'm sorry for all the scrolling. I need to find where I was. Where was this? All the way up at the top, we had r equals 0.99. And I drew here a line that was a slope at 1. And I said, look at how closely that fits the yellow line. But that was actually not the best line. In retrospect, we should be suspicious. That blue line, if you look at it really closely, it's really close to the yellow line. But actually, the best line would have been yes. I have to rerun all these. Okay. All right. So in the example above, I drew a line, a blue line with slope 1, but actually better would have been a blue line with slope 0.99 because the data was generated to have correlation coefficient 0.99. And so, oh, my demo is failing. What am I doing wrong? What I'm doing wrong is I didn't regenerate the data. Okay. Okay, I'm sorry. There's the data with 0.99. We'll let the code finish running. And with R equals 0.99, the better line to have drawn would have been slope 0.99. Okay, so I have just showed you two ways of making predictions. One way is with nearest neighbor prediction, nearest neighbor regression. And that's not guaranteed to give you a straight line. That will work for any kind of association. And the other is we try to find a straight line that's a good prediction line, that's guaranteed to be a straight line, and that's called linear regression. If you don't know whether you have a linear or a nonlinear association, then nearest neighbor regression is reasonable. But there are many situations where we suspect there will be an association, and we suspect that if there is an association, it'll be a linear association, like the association between square footage of my house and the price of my house. The more square feet you expect, the more the price of the house, and that there's probably a linear association there, that maybe every additional square foot adds to the price of the value of my house by $1,000 or something like that. So in that case, it would be better to have a prediction line that's a straight line. And if I can find a straight line, I'll probably have a better fit to the data. So that's when we use linear regression. So linear regression is all about finding a straight line that you can use for prediction. So it is a relationship between the X and the Y values. And we use standard units here when we compute it. It's very handy to convert the data to standard units. All right. So the equation, I've tried really hard. We've tried so hard to avoid inundating you with equations, but I apologize. We got to do a couple of equations here to talk about linear regression. So the equation for the linear regression line is the Y value is a linear function of the X value, means some constant times the X value, like Y equals 0.5 times X or Y equals 0.8 times X. And that constant is the correlation coefficient. This pattern we just saw, the slope of that best fit line was, it turned out, equal to the correlation coefficient. And that was not just an accidental pattern we saw. There's actually a mathematical theorem one can prove that says in some very precise way, that is the best line you can use. And we're not going to prove it in this class, so you just have to take it on faith from me, that the slope of that best line is given by R, the correlation coefficient. So the equation for that best fit line is Y equals R times X. But there's something I have to clarify about this equation. In this equation, it's very important that Y and X are measured in standard units. So this formula will work if Y and X are in standard units. It won't work if they're not in standard units. So what this equation tells me is it tells me if I increase X by a certain amount, how much will Y increase? If I increase X by 1, I predict that Y will increase by about 1. This lets me make predictions. If I have a known value of X, but I don't know the value of Y, I can use this equation to make my best guess prediction for what Y will be. This is a line that we expect to hold on average. Okay, so don't expect every point to fall on this line. The point is, this is the best prediction we can make, so points will probably fall near the line. All right, so this is the equation of the linear regression line. This is a formula. You can find textbooks that will derive this formula, but this is the result of the derivation. So I said there's some equations. I have to do some more equations, but I'll show you some pictures to help you understand if this is confusing. I showed you the equation for the regression line if you work with X and Y in standard units, but typically our data is not in standard units. So I would like to know the relationship between X and Y in the original units. not standard units. And here's what the equation looks like in original units. I said y was equal to r times x, but that's y in standard units and x in standard units. So remember the formula for what y in standard units is, or what x in standard units is. The formula for x in standard units is the value of x, subtract off the mean of all the x values, and divide by the standard deviation of all the x values. That's how you convert from original units to standard units. And similarly, you do the same conversion for the y values. So I just plugged into the equation I had before with my equation for how you compute standard units from original units. All right. So this line can be expressed by a slope and an intercept. You can rearrange the terms and put it into the form y in original units is equal to some constant times x plus some constant. The constant you multiply x by is the slope of that line. The constant you add is called the intercept. Okay, so if we draw the regression line through a bunch of points, this is your best prediction line, your line of best predictions. Then in standard units, the picture will look something like this. Your dots here are the data points. This line here is the regression line that you get with this formula. 0, 0 is the center of this diagram. The center of this diagram is a point with x in standard units being 0 and y in standard units being 0. The line goes through the center. It always goes through the center. The linear regression line always goes through the center when you're in standard units. And the slope of this line is given by r, the correlation coefficient. Okay, so that's just something you have to take on faith. Hopefully the demo gave you helped you see that pattern and helped you believe that this is a plausible relationship. And it turns out that this is the best line you can use. Now, if I convert that back to original units and I graph the data in original units, it'll have the same shape, but now the x-axis and the y-axis are in the original units, not in standard units. The regression line will still go through the center, but now where's the center? It's not at 0, 0 in the original units. In original units, the center corresponds to the mean of x and the mean of y. So that's the line goes through that point with the mean of x and the mean of y as its coordinates. And it has some slope. And what's the slope? The slope, it turns out, well, when I do this transformation, I'm shrinking or expanding. When I convert from original units to standard units, I shrink. When I convert from standard units back to original units, I expand. How much do I expand by, or how much do I shrink by? By the standard deviation. So the y values, when I convert from original to standard units, shrink. You divide by the standard deviation of y. When you convert back, they expand by the standard deviation of y. The x units shrink by the standard deviation of x. When you convert to standard units, when you convert back, they expand by the standard deviation of x. So a difference of 1 in standard units becomes a difference of the standard deviation of x when you expand into original units. And in the y side, a difference of r in standard units when you expand becomes a difference of r times the standard deviation of y. So that means the slope of this regression line is given by r times the standard deviation of y divided by the standard deviation of x. So what we obtain is the following equation for the linear regression line. Your prediction for y is given by the slope times x plus the intercept. The slope is given by the correlation coefficient multiplied by the ratio of the two standard deviations. And the intercept is given by this equation here. So if you want to know what that line is in original units, you use this formula. Okay, so there's two separate formulas for that regression line. They're both equivalent. One formula is in standard units, and that's very simple. That's the formula we have back here. Here's the formula in standard units, very simple. And the formula in original units, not simple. Okay, we're out of time. Next lecture, we'll show you a bunch of examples of applying this theory we just built up. So just as a reminder, what we're showing you here is we're showing you how, if you have a linear association, to build up a prediction line that can help you predict the value of y given the value of x. Have a great weekend. Don't forget to turn in the homework, do your vitamins, and I'll see you in lecture on Monday.